Yes, now we are coming on next property. A minus A transpose is skew symmetric. In the previous I told A plus A transpose was symmetric. Now it is A minus A transpose is skew symmetric. We have to prove. So again we'll say let Q is equal to A minus A transpose. And we have to show this as a skew symmetric. So this implies we will take transpose on both sides. A minus A transpose whole transpose, which you should write as A transpose minus A transpose whole transpose, or I should say it is A transpose minus A. Minus will be taken common, so left is A minus A transpose. Is it your minus Q? Yes. So I got it, Q transpose is coming minus Q. What that indicate? This indicate Q is skew symmetric. Hence, Q is skew symmetric. Second part, A into A transpose is symmetric and A transpose into A are also symmetric. So again we'll take let R is equal to A into A transpose. Then I take R transpose, then it will come A into A transpose whole transpose. Then we have already done this property, A B transpose is B transpose into A transpose. So that means this has come out to be A transpose into A transpose, A transpose whole transpose into A transpose. And when you solve it, it will be A into A transpose. Is it your R? Yes. So R is symmetric matrix. Same way you can do this part also. Proceed it, take this as S and then prove it. You can do it easily. So these three parts, one I told you A plus A transpose is symmetric, A minus A transpose is skew symmetric, and A into A transpose is symmetric. A transpose A is also symmetric. Now we are coming on one more theorem. What that theorem says, if A is a square matrix, the theorem says if A is a square matrix of order n, then it can be expressed, this matrix can be expressed as the sum of symmetric and skew symmetric matrix. Every square matrix can be expressed as the sum of symmetric and skew symmetric matrix, and this expression will be unique. So this is the thing we are going to prove. You note it. A square matrix, each square matrix can be expressed as the sum of symmetric and skew symmetric matrix, and this expression will be unique. Unique means only one way we can express it. Now I'll prove it. A is given as Aij, order is n into n. This is a square matrix. So we start with this. A is half of 2A, I can write. Nothing wrong. A matrix we have started, square matrix. That can be written as half of 2A. Then I can write this as half of A plus A transpose plus A minus A transpose. Nothing wrong in it. Half of A plus A transpose plus A minus A transpose. Or you can write this as half of A plus A transpose plus half of A minus of A transpose. Nothing wrong in it. Let this be taken as P, this will be taken as Q. Now we have to show that P is symmetric and Q is skew symmetric. So we start with this. Let P is half of A plus A transpose. Then what will be P transpose? It will be half of A plus A transpose whole transpose. half will be going out, left is A plus A transpose whole transpose, because you have done this property, Ka transpose will be Ka transpose. And then we can write half A transpose plus A transpose transpose. Or you can write this as half of A transpose plus A. Or it is nothing but half of A plus A transpose. Is it your P? Yes. So P transpose is coming symmetric. Same way you start with Q. Q is half of A minus A transpose. Then I'll take Q transpose, it will be half of A minus A transpose whole transpose. Half goes out, left is A minus A transpose whole transpose, or it will be half of A transpose minus A transpose whole transpose, or it can be written as half of A transpose minus A. Then we will take minus common from it, half of A minus A transpose, so it is come out to be minus Q. So what will indicate? It is skew symmetric and this is symmetric. So that means yes, A can be expressed as the symmetric and skew symmetric matrix. Every matrix A, square matrix, can be expressed as the sum of symmetric and skew symmetric. What will be the symmetric part? Half of A plus A transpose, and half of A minus A transpose will be the Q matrix. Now, one more thing they can ask, it is uniquely expressed, means only this is the way we can express the matrix as a sum of symmetric and skew symmetric. We'll do that also. In this case, what we do here, if possible, I'm saying contradiction, I'm just taking contradiction. If possible, let A is represented by R and S. I'm not saying symmetric or skew symmetric. What I'm saying, let A is equal to R plus S, where R is not half of A plus A transpose. We don't know this. So we will write in this case, if possible, let A is equal to R plus S, where R is symmetric and S is skew symmetric. And we have to show that R is nothing but A plus A transpose half, and A minus A transpose half will be S. So if I show that R and S are nothing but the same half of A plus A transpose and half of A minus A transpose, it will be uniquely expressed. So let A will take, if possible, A will write as R plus S, where R is symmetric and this is skew symmetric. So then we will say A transpose will be R plus S whole transpose. That indicate A transpose will be R transpose plus S transpose. And as R is symmetric, that means R is equal to R transpose. S is skew symmetric, that means S will be minus of S transpose. So what I should write here, this will be R only and this will be minus S. That means I got A transpose is this. What was A? This is equation 1, this is equation 2. Now when you add it, A adding equation 1 and 2, A plus A transpose will be what? This and this, it will become 2R, or we should say half of A plus A transpose is your R, and subtracting 1 and 2. Then what I get? A minus A transpose will be twice of S, or I should say half of A minus A transpose is your S. Is it coming as P, which you have done earlier? This is coming Q. That means R is nothing but P. S is again nothing but Q. What that indicate? Yes, R and S is nothing but P and Q, means only one way we can express a matrix as sum of symmetric and skew symmetric. What that is? Half of A plus A transpose and half of A minus A transpose.
So that you should keep in mind. This is an important theorem. One question will also come on this theorem that we'll take in next lesson, next video.